Okay, we're going to have a look now at specific and latent heat capacity. It's the beginnings of thermodynamics, and both of these equations are they're given to you in the formula sheet, so you don't need to remember them. One easy way to remember this is kind of similar to Einstein's famous equation E equals mc squared, although it's not square, and we've got this weird symbol here. We've got delta. This means change. And the theta in this case isn't angle, this is the temperature, so the change in temperature measured in degrees Celsius, although Kelvin you could use because the intervals are the same. So this is used to figure out the amount of energy it takes to heat up a certain mass, a certain substance by a certain amount. And then the next equation here, this is used in change of state, as we'll see. So instead of melting or freezing if we're going the opposite way, the latent heat of fusion refers to changing a solid into a liquid. And then we also have the latent heat of vaporization, which is when we turn a liquid into a gas. So the definition of specific heat capacity, it's an amount of energy that's needed to raise the temperature of 1 kilogram of a substance by 1 degree. It's really how much energy something can store, how quickly it can heat up. Now, you do need to know the units for all these different quantities. The weird one is this one here. Now, I know that some people like having their formulas done in triangles, so if that was the case, E would be at the top, and it would look something like this, okay? Now, this also helps you figure out what the units are, because we would have joules, energy, above, or in this case, divided by the unit for mass, and the unit for temperature. So we've got temperature and mass here. And then we have change in temperature here, obviously. So that is specific heat capacity. Latent heat is the amount of energy, and this is very important, needed to change the state of a material. Effectively, solids are held together by bonds, and they need to be broken in order for it to turn into a liquid or made weaker. So it's an increase in potential energy and therefore internal energy. Internal energy is essentially total energy in a system. But importantly here, you'll notice that the temperature here stays the same, okay, whether we're turning from a solid to a liquid or a liquid to a gas. So this is a sort of graph that you'll be expected to analyze, and notice what's on our graph, because unless you read what's on the axis and you're careful with the units, it's very easy to make mistakes, okay, and misinterpret things, especially in things like motion graphs. So we have a temperature and energy supplied graph, and temperature on the other side is in Kelvin. The intervals are the same. And we've got these different points, these different phases in the graph where something interesting happens. And you can tell this is for water because the freezing or melting point is at 0 degrees Celsius and the boiling point is at 100 degrees Celsius. So at A, we're heating up ice. Now it's gone from very cold here, minus 100 degrees Celsius, to 0. And we've heated it up until it begins to change state, making this the latent heat of fusion, this phase here. Okay. Then we are heating up a liquid from 0 up to 100, up to boiling point of the water. That is where we reach the latent heat of vaporization, this long straight bit here. Now, a common question is, why is this section here so much bigger than the latent heat of vaporization there? And it's because of bonds, potential energy essentially. There's very strong bonds in a liquid. There's still bonds in a solid, but they're slightly weaker, so it doesn't take that much energy. But in order to break these bonds or increase the distance between the particles, between C and D, turning it into a gas, takes an awful lot of energy because you're increasing the kinetic energy of the particles of water, and you're breaking the bonds essentially. And then after that, we're up to E and heating up a gas. These are the two equations. Basically, if the graph is flat, you would be using this equation at either point, B or D. If the graph is at a gradient, we can see there's a change in temperature. Okay, and you'll quickly find out when you try and do the equation, there's a change in temperature here, which means we're using the specific heat capacity equation. So, first problem. In order to figure out the specific heat capacity, we need to use the top equation here. Okay, so if we rearrange that, we get C is equal to energy, the amount of energy supplied over mass times the change in temperature. Now, it's handy to write the brackets on here because sometimes you can divide E by M and multiply that, by the change in temperature. So make sure that bottom is in brackets if you're putting in your calculator. Now, the mass that I'm going to say, and this is just a random number, we're going to use 0.8 kilograms. So remember the energy is in kilojoules here, so therefore C is equal to the change in energy. And I'm going to use this section here, okay? So this here, if we go down, that's about 550, and then here, that looks like it's gone all the way down to about 950. So 550 to 950 is 400, and because it's kilojoules, you can either use another 3 zeros, because 1 kilojoule is 1,000 joules. I'm going to use standard form because if I swap the K out for this power, and put that in my calculator, I just find it a bit easier. So you can either write 400,000 or 4 times 10 to the 3. The mass, we've already established, is 0.8, and the change in temperature is from 0 all the way up to 100, so a total change of 100 degrees Celsius. So when I put that through my calculator, you can hear me tapping this away in the background, 400,000 divided by, open brackets, 0.8 times 100, that gives me an answer in this case of 5,000, and that will be joules per kilogram times degrees C. So there's my final answer for there. Now that's not actually accurate, so maybe I should have used a different mass, but the maths makes sense. Actual specific heat capacity of water is about 4,200 joules per kilogram. But in terms of how to do this problem, this works just fine. Right, now what we're going to do is we're going to work out the latent heat of fusion of water. So we're going to use this equation here. Fusion is when we turn in from a solid to a liquid. Okay, so rearranging that equation, so the latent heat of fusion will be equal to the energy supplied divided by the mass of water. You're changing from ice into liquid water. So the mass, we've already established, is 0.8 kilograms. No need to convert from grams there. We should be using kilograms, but the energy is in kilojoules. So the energy goes from here, which is a bit of a curve there, is 200 to 550, but we need to remember it's in kilojoules. So 200 to 550 is 350 kilojoules. And if we type that into the calculator, 350 kilojoules or 350,000 joules divided by 0.8 kilograms gives me a total of 437,500. And the units here will be joules over kilograms, so it will be joules per kilogram. So 437.5 kilojoules per kilogram. And now we're on to the latent heat of vaporization. So we're still using this equation here, and we've still got 0.8 kilograms of water. And don't forget the energy supplied is in kilojoules. So the latent heat of vaporization as we turn a liquid into a gas, in this case, and remember the temperature stays the same, so that's a big dead giveaway that it's not this equation here. So that will be the energy supplied over the mass. The mass is still 0.8. Now the energy supplied, it's easy to read off graphs using a ruler in an exam. So if you slide your ruler along, should be able to get to here, and that is 950 kilojoules. And up here, the graph's not very clear, so I'm going to make the assumption that it's 3,200 kilojoules. Now the difference between those two is 2,250 kilojoules. So punch this in your calculator. 2250,000 or times 10 to the power 3 divided by 0.8 gives me 2,812,500. And in case you can't remember the units, you can get them from the equation. We will have, what have we got here? We've got energy in joules, we've got mass in kilograms. So the units will be joules divided by kilograms. So this is the latent heat of vaporization of water in this case. Right, this is a problem for you to do, and you've got to find the specific heat capacity, the latent heat of fusion, and the latent heat of vaporization using this energy temperature graph, and you can see the changes in state here. So using the two equations that we had before, we're going to go for a mass of 0.5 kilograms. Right? So use those two equations, pause the video, and see if you can work out the latent heat of the specific heat capacity, the latent heat of fusion, and the latent heat of vaporization. So if you want to have a shot at trying this for yourself and seeing how you're doing, now is the time to pause the video. And if you didn't pause the video, you're still listening. If you did, here's the solution. Specific heat capacity, so rearranging the equation, and you can put this in brackets, gives us a change in energy, and it's just in joules this time, so it's pretty straightforward. Using this section in the middle, we've gone from 800 to 1800, so it's 1000 divided by 1.5 times a temperature change of 50. We've gone from minus 30 to 20. That's a total of 50 degrees Celsius change. Gives us 13.3 joules per kilogram per degree C, or not per degree C, degree C. Latent heat of fusion, L equals E over M. We've got the mass, the energy for fusion, which is here. This is the latent heat of fusion. That will be 400 over 1.5, which gives us 267 joules per kilogram. And then up here we have the latent heat of vaporization. Same equation. The energy supplied was 600 joules between here and here. Divided by 1.5 kilograms gives us a final answer of 400 joules per kilogram.